Hello. In the past few classes, we have been looking at the semiconductor, the p-n junction, various characteristics of the kinds of materials that are involved, what happens when you put them together, what parameters we have to be cautious about, and so on. And we also looked at how the material is even manufactured. How do you start off with essentially sand and arrive at something that is single crystal silicon or polycrystalline silicon or even amorphous silicon. And then the idea that you take this and then you make your p-n junction, and so that is something that we seem to think was necessary. So what we would like to do today is to look at this p-n junction a bit more and to see how this junction responds to the arrival of radiation. So in the end we are going to use a p-n junction as a solar cell. So what we will see today is how does it function in the context of solar radiation incident on it, and therefore why is it that you need that p-n junction for it to work as a solar cell. Okay, so that is the idea that we will pursue through this class. So we are going to look at the learning in terms of learning objectives. We are going to describe the interaction of a p-n junction with radiation. Okay, so a p-n junction, how does it interact with radiation? Once radiation is incident on it, what are the phenomena that are occurring in it, and what is the consequence of that phenomena? And in that context we would like to explain the functioning of a p-n junction solar cell. So that is the basic idea that we would like to pursue through this class. Okay, so we actually did some work on this p-n junction, understanding how it behaves. I will just highlight one or two key aspects of it, specific aspects of it, because that is how we will be able to continue with the description we will see in this class. So we spoke about the idea that once you make the p-n junction, there is a transfer of charge from one side to the other and from the other side to this side, and you end up creating this depletion region or the space charge region, and then that you can actually do a forward bias of it. So, once you create this p-n junction, it has certain characteristics. In terms of, when I say characteristics, in terms of how its current and voltage will change depending on what conditions it is placed in. This is you can think of it as information that you can learn independently, but often that is how it is taught. Often that is how you see the p-n junction and its IV characteristics, etc. But it is not just an independent scientific curiosity kind of thing on what a p-n junction will do, but really those characteristics are critical in explaining how it functions as a solar cell, and that is why we are spending some time trying to understand those characteristics. So in fact you do have this exchange of charges because of the way in which the energies line up, and you create this space charge region or depletion region, which primarily means that on each side of the junction, whatever was the majority carrier is missing for a small distance. Okay, so it is exaggerated here as a little larger distance here, and similarly a larger distance here, but you are really looking at a very thin region across the junction where the majority carrier. So in this case we have the n side here and we have the p side here. In keeping with the p-n name, p-n junction, most of my diagrams are with I have been trying to keep it consistent with p on our left side and n on the right side, so that it is easier for you to follow. So on the n side the majority carrier would have been an electron, on the p side the majority carrier would have been a hole. When you create this junction, because the holes do not see enough holes on the n side, they drift into the, they diffuse into the n side, and the electrons do not see enough electrons on the p side, so they diffuse into the p side. So that is basically what you are seeing. And in fact as I said once in one of our earlier classes, when we looked at the metal, the electron can actually roam all over the metal because you have the same ionic core everywhere, and therefore it can roam everywhere without any restriction. Whereas in this kind of a situation where you have a p-n junction, the electrons as they roam into the p side are seeing a different background condition. The holes which are moving to the n side are seeing a different background condition, so they cannot indefinitely move, they are charged. So the region they move into is no longer charge neutral. They are building up a charge in that area. It is no longer charge neutral. It was charge neutral to begin with, but since they are arriving at that region with a different charge, they are actually changing the charge neutrality of the region, and that is why this is actually called a space charge region. This entire region is called a space charge region because it is building up a charge there, and that is the reason why the holes do not diffuse all the way across into the n side, and the electrons do not diffuse all the way across to the p side, and that is how this differs from this being a metallic sample or even a junction between two metals. So, even there you will have some build up, but that is okay, maybe that is not the that also has some aspects associated with it, but let us say two pieces of the same metal which are put together, then you can actually have essentially the electrons freely roaming around. So, this is how the build up is there, and having put this together, you can attach a battery to it. So, now clearly because you have put charge on either side of it, I mean not put, it has automatically redistributed its charge and created this space charge region. So, there is an inbuilt potential that has been created. You can put a potential outside of the sample which can counteract this potential or build on this potential. Okay. So, this potential that builds inside this sample or the field, which would actually be from the positive to the negative. So, the E field would be this way. So, this potential is preventing further flow of charge, right. So, you can put external potential to this sample which either assists this potential, in which case it makes it even more difficult for charge to get transferred across this junction, or it counteracts this potential and makes this potential essentially ineffective or less effective, and then eventually charge can go across it. So, we basically can put what we would call as the forward bias, which means we are putting the positive side of the battery, external battery, in contact with the p side of the sample, and the negative side of the battery in contact with the n side of the sample, right. So, we are pushing more electrons into the n side, and we are drawing away electrons from the p side, which means effectively like we are pushing more holes into the p side. So, as we discussed, what this does is that it basically reduces the space charge region. So, it starts pushing more holes this way, it starts pushing more electrons this way. So, that therefore, the space charge region begins to decrease, and once you cross the potential that corresponds to this space charge region, essentially you will have current steadily flowing through this p-n junction, and in the context that we traditionally associate current, the conventional current is associated with positive charge. This is the direction of flow of current, of conventional current. The direction of the flow of the holes is the direction of the flow of the conventional current, electrons are flowing the opposite way. So, you can think of it this way, electrons are coming this side and they are getting consumed by the holes coming from the other side, and hole essentially means it means the sample is charge neutral, but the bonds can actually accept one additional electron, right. So, that is what we mean by saying that there is a hole there, and so this electron that is coming from the n side, as it crosses across the boundary and goes into the p side, it is actually going into that location where that one additional bonding electron was not available. So, it is readily accepting that electron. So, the electrons are actually steadily flowing from your right to left, and because there are, as it sits in that location, one more hole arrives, one more electron arrives, and it keeps occupying locations, and therefore, you can think of it as a current that is flowing. Okay. So, one way they describe it is that they are all coming and getting annihilated at the junction. The other way is you can think that there is a steady flow of electrons, and which is being compensated by electrons being drawn away there, and therefore being replaced by holes again and again. So, every time you put an electron into the p side, you are also removing an electron from this side, right. So, electron is entering from the right side and it is exiting out on the left side of our sample. You can think of it that way. So, if you remove an electron, it is the same as having added a hole there. So, you were short of one bonding electron was missing there, and one electron crossed over from the n side and occupied that site, and then you took that electron all the way to the left end and took it off the circuit, and therefore you have essentially reintroduced that hole, that place. So, that is why that description you keep hearing of holes coming from the left, electrons coming from the right, and they are basically annihilating each other in the junction. It does not mean matter is being destroyed or some some energies, some nuclear activity is going on there. That is not what is happening. It is just that this is the description that captures the activities that are happening there. But you can also think of it, if you really want to not to confuse yourself, you can think of it as an electron that is going through and through and through. As it crosses the junction, it occupies the location that was available where there was a hole, which means that hole now disappeared. That is basically what we mean. So, that hole is no longer there because an electron is now sitting there. But you slowly draw that electron away to your left, and you remove that electron from that region, you have again brought back that hole. That missing bonding electron is still there. So, you have brought a hole. So, each time the electron hops from one hole to the other hole, it is the same as that hole having hopped this way. So, you have a one hole, one electron, electron goes this way, it has cleared this location on your right hand side. So, you have let us say one hole here which I put as a positive H, and I put an electron here E minus. So, if this switches here, then this location now has the electron, and this region which it left goes back to being a hole. So, that is essentially what it means. So, every time an electron moves from left to right, it is the same as the hole moving from right to I am sorry, from every time an electron moves from our right to left, it is the same as the hole moving from our left to right. So, that is what we mean, and so you can think of the circuit that way and also understand what is going on. So, anyway, so this is what is happening if you forward bias the sample, and so this junction will disappear and you will have a steady flow of current. So, that is the idea of this PN junction in forward bias. Please note that when I said forward bias, to show that as an experiment, we put this battery here. Okay, so, we put this battery in this external circuit, and we deliberately connected the positive to the P side, the negative to the N side. So, this is what we did to demonstrate this process, to demonstrate this characteristic of this PN junction. But in reality what has happened? In reality what has happened is we have pushed electrons to one side of the PN junction, and we have pushed holes to the other side of the so if you want to call it H plus as the hole with the charge, and we have pushed that on the P side of the sample. Okay, so or we are drawing electrons out that side, so therefore, you are pushing holes into this side. So, you can put it that way. So, the point that I am trying to make is that when we say something is in forward bias, when we say PN junction is in forward bias, it basically means we have electrons, additional electrons from an external circuit or from anywhere, additional electrons appearing on the N side, additional holes appearing on the P side. Okay, so anytime you create a situation where initially you have a PN junction which is sitting there, and because it is a junction is formed, you had the space charge region being developed, you had this depletion region being developed, and that happened as soon as you made your PN junction, right. So, that is your starting point. From this starting point, if you do anything to the sample which creates more electrons on the N side and more holes on the P side, you have essentially created a situation which is similar to what you are seeing on your screen, which is you have created a forward bias. Okay. So, that is the point I wanted to keep in mind. So, it does not have to be through a battery. In this case, we are showing this example by putting a battery outside and doing the connection, but that is not necessary. You create a situation where there are more electrons sitting on the N side and more holes sitting on the P side. When I say more with respect to what were present when you initially formed the junction. When you do more, you have created a situation which is similar to a forward bias, and therefore, at that point the PN junction will show you this behavior that you just saw of what it is going to do during a forward bias. Okay. So, that is something you keep in mind, and we will get back to it. So, as we saw that because of the space charge region, you will get this negative charge here, you will get this positive charge on the I mean the N side of the sample. This is the P side. As we said, this is charge neutral here. So, charge neutral, so negative and positive, and because of this relationship we find that E has a linearly decreasing characteristic from where this region begins and goes to a fairly low value here, some appropriately low value here, and then since the slope suddenly becomes positive here, the rho becomes positive here, this is rho, this is rho. So, negative rho becomes suddenly positive rho, and therefore, in your equation the slope is now suddenly positive, this slope is now suddenly positive, and therefore, from this lower value the slope keeps increasing, and then you arrive at this neutral value where suddenly again the rho is 0, because then once the rho is 0, the slope rho by E, rho by epsilon becomes 0. So, here rho by epsilon is positive, rho by epsilon negative, rho by epsilon 0. Okay. So, because it is 0, you have a flat line here, it is negative, so you have a negative slope, it is positive, so you have a positive slope, it says it is 0, so again you have a flat line here. So, this is basically the behavior we see, and then correspondingly if you look at the potential as you go from left to right, you find that if you look at this relationship here, then you see that the slope is essentially related to minus E, and E itself is 0 here. So, E is 0 here, and then E is decreasing. Okay. So, if E is decreasing, minus E is increasing, okay, and minus E is increasing means the slope dou V by dou x is increasing. Okay. So, it is continuously increasing, that is what you see, the slope is steadily increasing, right. So, the slope is continuing to increase, and then you cross this origin. So, you suddenly see here E is basically increasing, implies minus E is decreasing. Okay. So, minus E is decreasing, because minus E is decreasing, the slope having reached some value now starts decreasing. So, the slope starts decreasing. So, it starts decreasing like this, and then once you reach this region, again once you reach this flat region corresponding to this point here, E has become 0. Okay. And so, once E is equal to 0, the slope is 0 and you again get a flat line. So, this is the behavior of this junction in its static state as soon as it has been built or once it is in that kind of a stable situation. Okay. So, this is the characteristic, and we saw what would happen if you take this and then you put forward bias to it. And again if you take the same thing and you do a reverse bias, which means you are now taking the negative side, I am sorry, the positive side and connecting that to the N side, and you are taking the negative potential here and connecting that to the P side, okay, as opposed to the opposite that you saw here. We are doing the opposite here, we are taking the positive and connecting to the N side, whereas previously you had the positive connecting to the P side, and here you are taking the and previously you had negative connecting to the N side, you now have the negative connecting to the P side. So, what is happening? You are pushing more electrons in here and you are pulling out electrons from here. So, when you pull out an electron, you leave behind a bond that is unsaturated. Okay. So, essentially you have added a hole. So, that is basically what happens. So, you are increasing the number of holes in the N side of the sample, you are decreasing the number of holes on the P side of the sample, because you are pushing electrons in, you are pushing electrons in, it will go, it will travel through and through and through, and it will reach a point where it till it hits some other electron and it is not able to go forward, it will go, it will continue to go there, and it will because you are pushing it, and it will go there and it will occupy that site which was a hole. So, you are increasing the number of electrons on the P side and you are increasing the number of holes on the N side. Naturally, you can expect that the number of this region which was positive will now increase a little bit, and the region that was negative here will increase a little bit. Okay. So, that is called reverse bias, and so that is essentially what you see here. So, this region has now increased because you pushed more electrons in and you pulled away more electrons from here, essentially pushing holes in, and therefore, this region also went up. And clearly this is acting as a barrier, it is it is opposite to the flow of the electron. So, it is resisting the this process. So, this is called reverse bias, and it basically means that it is going to prevent flow of electrons as much as possible. You can continue this till you close off all the holes that are remaining on your P side and all the electrons that are remaining on your N side, and then you will be able to force a current through this sample, right. So, you can force a current through the sample if you do that, and but that point you have actually sort of broken down this material at some fundamental level, and you are pushing this electrons through that sample. So, that is the reason why we get this characteristic. When we go in forward bias, we quickly run out of the with small increase in potential, we counteract that built in potential that is there due to the presence of that space charge region, and then you start having a steady increase in current with increase in voltage. In the reverse bias, as you keep increasing the voltage, the sample keeps on resisting it also increases its resistance to the voltage that you are applying, and then so steadily that so it does not really prevent does not really allow much current through the sample. It takes whatever little charge you put in, it just holds the charge there and resists further charge coming in, till eventually you max out that junction and the sample, and then it breaks down, and then you have this high current flowing through that sample. Okay. So, this is the forward bias and reverse bias characteristic. The only thing I will again alert you to before we move forward is the fact that although in the description we gave we used an external battery to enable this, that is just for our understanding of the process. The key idea is where is given that you have a p-n junction, where are you adding, where are you forcing in or creating more electrons, where are you creating more holes. So, depending on where you are creating more holes and more electrons, correspondingly you can think of the junction being forward biased or reverse biased. Okay. So, that is the idea that I would like you to keep in mind. Okay. So, with this in mind, we will now look at the characteristics associated with the energy band diagrams of that p-n junction, because this is where we will have to understand what happens as the radiation comes in. So, if you look at this, we discussed this earlier, that when you simply have a conduction band and a valence band. So, this is valence band and that is conduction band, and you have a band gap Eg. Okay, so, that is a fixed band gap across the sample Eg. So, when you have Eg equals h nu, you have some incoming radiation, Eg equals h nu. When you have Eg equals h nu, you can have an electron transition, and you will have an electron sitting here, you will have a hole sitting here. So, this is what will happen when you have incoming radiation. At that point, I indicated to you that when you do this, you are creating a situation where the electron and hole are in physical proximity. Okay, so, in the sense that this hole and the electron are essentially physically in the same location, they have just the electron has simply moved up in energy to a value across the band gap. So, if you give it enough time, the electron will simply decay down, and it will come back down and it will occupy that spot that it vacated, and the material will go back to being its old self before the radiation came to it. So, therefore, when you simply take a semiconductor, even though we say semiconductor has a band gap and then therefore it can absorb some radiation and all that stuff, even though we say that, if you simply take a sample of a semiconductor and keep it out in the sun, you are not really going to be able to capture any electricity out of it. It will do the transitions, but the transitions will simply reverse, and at the end of it you will not really be able to capture any electricity. So, we have to do something about ensuring that you are decreasing the chances that the electron can fall back into this hole that it created. Okay. And to do that, we essentially have to move the electron to some other location, move the hole away to some other location, and in that process physically it is no longer that easy for them to just like that collapse into each other. It does not drop that to 0%, but it decreases it dramatically. So, this is called charge separation. You have to separate the charge and stabilize it. So, it has to get separated from these locations, and only then it will get stabilized. So, that is the point we would like to understand with the perspective of this diagram. So, we looked at it as again the same thing, p-n junction. So, this is p side, this is n side. So, for the n side, for both these samples, assuming that we started with the same semiconducting material, their original intrinsic Fermi energy EFI. So, that is what I am calling as E subscript F for Fermi energy, and subscript I saying that it is the intrinsic Fermi energy, is that is the energy, Fermi energy of that material if it had got no dopants, was this particular value. Okay, so, that is the value that you see here. So, that is the Fermi energy value that you have. Now, because on the p side you put in some dopants, you created some acceptor levels which were here. So, those acceptor levels were available here, which made it easy for electrons to go to those acceptor levels, and similarly on the n side you put in some donor levels. So, donor levels showed up here, and so that again became easy for the material to perform get charge carriers into the system. So, now given the way the Fermi energy is defined, essentially the Fermi energy of the n side of the sample moves to this donor level, and the Fermi energy on the p side of the sample moves to this acceptor level. Okay. And so on the p side the Fermi energy came down, on the n side the Fermi energy went up. And when you put these samples when you connect the two samples, because of equilibrium requirements for equilibrium, these two energy levels line up, they line up with each other. Okay, because and that becomes the defining parameter for that sample, the fact that the Fermi energy now lines up across that sample. You took an n sample and a p sample and you joined them together, and the two of them now understand that they are in contact with each other, the Fermi energies level out, so that that is how the energy remains constant. So, it is just basically got to do with energy minimization. So, it minimizes the energy, and this is how they end up minimizing the energy, the Fermi energy, and the fact that the chemical potential on either side should be the same, and this is how it ends up being in contact. Okay, so, this is the situation we have, and on this sample let us say we have incoming solar radiation. Okay, so, we have incoming solar radiation. So, in some ways you can still think of it as a transition occurs, you create holes and electrons, holes on the valence band and electrons on the conduction band. So, that is basically what I am showing you here. There is incoming solar radiation, this radiation, so this is also incoming solar radiation. Right. So, incoming solar radiation on both sides of this junction, and you create this holes down here, you create these electrons up here, holes down here, electrons up here. Okay. So, this situation we have created. Now, we see an interesting situation. The interesting situation we see is that we have holes sitting at two different levels. Okay. The Fermi energy is what leveled out, Fermi energy is flat, but the band structure is not flat. The band structure is not flat. Fermi energy is flat across the sample, band structure is not flat. The conduction energy, the conduction band, the lowest energy level of the conduction band of the n side is sitting here. The lowest energy of the conduction band on the p side is sitting there. So, the lowest energy level of the conduction band is not the same if you go from left to right. Okay. So, the conduction energy band lowest available energy level is high on the left side, it is low on the right side. Okay. So, that is the idea we have. So, this is called band bending, the idea that in the middle you have this situation where the band is actually bending from one level to another level, right. So, this is band bending that has happened. So, so these two are not in the same level. Similarly, you look at the valence band energy level. So, the valence band energy level on the, so this is the highest occupied energy level on the if you set aside the the impurity levels with respect to the intrinsic material, this is the highest occupied energy level on the n side of the sample, and this is the highest occupied energy level on the p side of the sample of the valence band. So, clearly they are also not at the same level. The highest occupied energy level on the valence band on the p side is high, the highest occupied energy level on the of the valence band on the n side is low, and so it has to bend down and go. It starts off, bends down and goes. So, that is basically what we have. Now, given the nature of the electrons and the holes, the electrons basically are negatively charged, and in the context of this energy diagram will tend to go to the lowest negative value, lowest energy level that they can find. Okay. So, they will naturally slide towards the lowest energy level they can find. So, so this they tend to slide down, and the holes on the other hand, given that they are positive charge and essentially they represent an absence of electrons, will try to move to a high level so that the electrons can go to a lower level. Okay. So, the electrons will in this diagram is set up with respect to electrons fundamentally. So, as the a hole moving up in energy level is essentially equivalent of an electron moving down in energy level, right. So, if all the electrons are moving down, you can think of the holes as moving up. So, therefore, in this situation, when you have created electrons at two different energy levels and you also created holes at two different energy levels, the holes try to consolidate. So, all the holes try to gather and consolidate such that they are holding the highest position possible. All the electrons tend to consolidate, get together and consolidate such that they are holding the lowest position possible. So, what this basically means is the electrons that are out here will try to come this side, and the holes that are out here will tend to try to go that side. Okay. Essentially trying to minimize their energy. This is basically what they are trying to do. To minimize the energy, electrons on which were holding a higher energy level will slide downwards, and to join electrons which are holding a lower energy level, and holes which were holding this lower energy level here, they are not necessarily going to higher energy level, but they are analogous to electrons sliding down. So, holes going upwards is the same as electrons coming downwards. So, these electrons will bubble up, so to speak, they will bubble upwards, whereas the holes will bubble upwards, electrons will slide downwards. So, this is basically what you are going to see, and that is how the sample now behaves. Okay. So, you initially formed a p-n junction and you already had a transfer of charge, okay, from one side to the other, and that is what created your space charge region, etc. Now, over and above that, you put solar radiation on it and you created more electrons and more holes, transition occurring on all sides, and then these electrons gathered together in one location, the holes gathered together in another location, driven by the ideas that I have shown you in this slide. So, once this happens, the diagram will evolve. So, if you want to look at it step by step, once this is the step of the radiation just having come and having created these electron hole pairs. So, once they consolidate, these electrons here would have gone down to this location and the holes here would have gone up. So, once you do that, you will have a situation which looks like this. Those electrons which were sitting here moved down and the holes that were sitting here moved up. Okay. So, we have this situation where the electrons have gone one side and the holes have gone the other side. So, now what do we have? We have an interesting situation. Again, as I said, if you go back to what we had previously just put down, we had one semiconductor and we had this transition. So, you had a hole here and you had an electron there, right, a hole here and an electron there, and this transition occurred, electron in the conduction band, this is the valence band. At that time I told you that if you do this there is an equal chance that the hole, I mean the electron will drop right back, because the hole and the electron are sitting right there and they can recombine, fine. Now what do we have? We have a situation where you did the transition, you created a bunch of electrons in the conduction band and created a bunch of holes in the valence band, but they are no longer in the same location. The holes all slid off to this side, the electrons all slid off to this side. So, you have greatly dramatically reduced the possibility that these electrons which are now on the n side of the sample will be able to combine with the holes that are sitting on the p side of the sample and annihilate each other. Okay. So, you have greatly reduced this chance, or at least it is not an immediate activity, it is not like immediately this is going to happen. You have given them a chance to stabilize, okay. And so, that is the key function that the p-n junction accomplishes. Okay. So, that is the key step that the p-n junction accomplishes, which an independent semiconductor such as what you see here is not able to accomplish. Okay. So, a single individual separate semiconductor is not able to accomplish this stabilization of the charges, which this p-n junction is able to accomplish because of the band bending that it has created, which has created a situation where all the holes agglomerate or accumulate on one side of the sample, all the electrons accumulate on the other side of the sample, and therefore, suddenly you now have a stable situation, it does not immediately collapse on itself, and that is how we are able to tap this for electricity outside. Okay. So, therefore, a p-n junction is a very essential part of the solar cell structure. So, a p-n junction is very essential to the solar cell structure, and so therefore, they use this device to create this situation. So, we have now got this, so this is again the p side and this is the n side. Okay. So, this is what we have accomplished. So, now I would also like to take a moment to tell you something about the orientation of the band diagram, because I think just the way you saw here what is happening with respect to the charges, what charges are going where and how they are stabilizing, it is good to also have a physical picture of what this is in terms of a solar cell that is that you are likely to see somewhere. So, when we look at a solar cell, we actually saw in our previous class as we manufacture the solar cell, you essentially have a disc, a thin wafer that is created, thin circular disc that is created, which is maybe let us say it is doped with p dopant in it, and then you do maybe ion implantation or you do surface diffusion or something, and you add a thin layer of n dopant on the top. So, it is a single crystal, let us assume we are talking of a crystalline single crystal solar cell. So, you have a solar cell where you have a top layer which is n doped and bottom layer which is p doped. So, this is what you see here would then be that solar cell, and this would be your p doped material, and on top we have this n doped material. We saw how it is manufactured, how the wafer is manufactured, and the idea that you can do either diffusion or ion implantation or epitaxial growth and end up getting this n doped material sitting on top of the p doped material with a very good interface. That is the most critical part of it. Okay. So, we have this structure and you have this band diagram. So, this band diagram corresponds to this structure. Okay. So, So that is how you need to associate these two. But one important point I want to draw your attention to, it may be a trivial point, but I think it is necessary for you to get a physical sense of this, so that you know, you can understand these diagrams better, at least in your mind. Please note that the band diagram that we have drawn is from left to right. So on your left we have the p type material, and on the right we have the n type material, whereas the solar cell that I have drawn is bottom up, right. We have p at the bottom, we have n at the top. So the orientation of this band diagram is different from, is 90 degrees away from the orientation of this solar cell the way we see it. So that is just something that you have to keep in mind. So in reality what is happening is, this is the orientation that you have to associate with this diagram, okay. You can use it any which way you want, but this is the orientation of the solar cell that you should associate as opposed to this horizontal orientation. You should associate this vertical orientation with this band diagram. So then you have it all lined up correctly. This is your p side and this is your n side. Similarly you have the p side here, and you have the n side here. N side here, right. So p and n are there, and that lines up with the band diagram that you are seeing here. Also in terms of scale, this is a very expanded band diagram that I am showing you from left to right for sake of clarity. Clearly this is all going to I mean, from p to n is of course going to be the extent of that sample that you have. We spoke about that being, you know, just about 0.2 millimeter or 0.5 millimeter or even less. Those are the wafers that you start with. You can even make it much smaller. And also this zone in the middle, the depletion zone, is going to be an extremely tiny zone centered along this the interface that you see here, right. So this interface that you see here, at that interface is where the depletion layer is going to exist. So so you are thinking of looking at a very narrow region. So please understand, keep in mind the orientation of the cell relative to the orientation of this band diagram, and the fact that, you know, the dimensions are all exaggerated, okay. So for sake of clarity, that is the reason why it has been exaggerated. So this is something that you should keep in mind, so that it does not confuse you, that, you know, why is it in one way and the other way. So solar radiation falling on this has created the situation that you have more holes on the n side of the sample and more more electrons on the n side of the sample and more holes on the p side of the sample. Now as I mentioned right at the beginning, when we spoke about the forward bias of the sample, okay, forward bias of a p-n junction, I told you that we basically put a battery there to create more electrons on the n side of the sample and more holes on the p side of the sample, and that created a forward bias for that p-n junction. But I also told you that that is not the only way you can do that. In any manner, if you create more electrons on the n side of the sample and more holes on the p side of the sample, more relative to what was there before that, shortly after the junction was formed, in all those cases you have created a forward bias. So if you look at the diagram that you have here, you have actually created a situation where the p-n junction is now in forward bias. So all that we discussed about the forward bias and reverse bias was not in vain. There was a purpose for it. So this is the purpose. The purpose is that when you actually use the p-n junction and you subject it to solar radiation, its natural position that it arrives at, the natural position that it settles into, which is what you see on the diagram in front of you, is a position which corresponds to this junction being in forward bias, okay. So that is something that you have to keep in mind. So when you use this sample as a p-n junction, what as I mentioned, there are a few things that we have to keep in mind. One is that we would like to minimize the recombination, okay. So recombination, as I said, will more easily happen when you have only a single semiconductor. It is much less likely to happen when you have a p-n junction, but it is not 0. So recombination will happen. In fact, it does happen even in a p-n junction. So recombination simply means you brought in this energy, you created some electrons on the n side, you created some holes on the p side. Hopefully you can tap this as an external electricity, but before you can tap it as an external electricity, internally itself the p and n are cancelling each other out, or rather the hole and the electron are cancelling each other out. So that is recombination. This recombination occurs much more when you have defects. Okay, so when you have defects, you have dangling bonds. When you have dangling bonds, it traps all these electrons and holes, and then it creates a situation where they more easily annihilate each other. So presence of defects is a bad thing in a semiconductor, and that is the specific reason why there is such interest in using a single crystalline silicon as the best possible, if you think within the silicon system, single crystal silicon is your is distinctly better sample for you to work with for creating a solar cell. But as I mentioned in our earlier class, that when you do single crystalline silicon, simply because of the process involved in creating it, it is expensive. Okay. So, your next bet is your polycrystalline silicon, but clearly that has grain boundaries, and that is the reason why it is called polycrystalline sample, and that has many more defects than single crystalline silicon. Naturally, many more of the electrons are annihilated within this, electron hole pairs are annihilated in that sample, and therefore its effectiveness is less. And finally, you have amorphous silicon, which is distinctly cheaper than the single crystal or polycrystalline silicon to make, and more than that, it is also very flexible, in the sense you can put it on any surface of any kind of contour and use it, and therefore there is lot of interest in working with amorphous silicon. But by nature, again, amorphous means those atoms have lot of dangling bonds and so on, and clearly there are more defects. Of course, we saw how hydrogen can be used to stabilize those defects, but nevertheless, it of the three, the single crystalline sample, the polycrystalline sample and the amorphous sample, the amorphous is the least effective in capturing the solar radiation in a manner that you can continue to use as a external power source. So, it is basically a trade off between cost and efficiency, okay, and with the idea being that you would like to minimize recombination. You will never eliminate it, but you will simply want to minimize it. Okay. So, this is something that we would like to keep in mind. Okay. So, if you look at this now that you have created this the p-n junction, and you have seen how you can separate out the charges, you can actually generate electricity. I mean, you can tap this, now that you have separated the charges, that is basically what it is. Even in a battery, that is what you have got a source of electrons, and those electrons will come through the external circuit and it will come to the other side. So, anode cathode you have, and then you have some process by which you utilize the thing in the external circuit. So, similarly with the solar cell, you have now created a situation by putting this p-n junction that you have separated the charges, and these charges can flow in the external circuit. The one important aspect of a solar cell that we have to keep in mind, which we will discuss in greater detail in one of our immediately succeeding classes, is the fact that a solar cell is a current source, okay, as opposed to most of the units that we get for from any other purpose, which happen to be voltage sources. So, when you buy a cell, a battery from a shop, which is an electrochemical device, that is typically a voltage source, whereas this is typically a current source, meaning that you are first generating the current, and then the voltage is whatever happens because of the current. Okay. So, the current is what drives the behavior of this sample, and this is because the charge carriers are being created by the sunlight that is received, and so essentially you first generate this thing called the photocurrent, okay, because of the incoming solar radiation. So, when you do not have any external load, so you have just put the solar cell out there, you just buy the solar cell, you put it out in the sun, you do not connect anything to it, you just put it out in the sun. When you put it out in the sun, you have created done exactly what I said, which is put more electrons on the n side, more holes on the p side, which basically means when you just take a p-n junction or solar cell and put it out in the sun without even putting any external load, you have created a forward biased solar cell. Okay. You have not connected a battery and done the forward bias, you just left it out in the sun. You left it out in the sun, it became forward biased because there is more holes sitting on the p side, more electrons sitting on the n side, not just more holes and electrons sitting there, there is solar radiation coming in, and that means it is creating even more, it is just continuing to create more holes and more electrons and on both sides of the sample, and the electrons are continuing to slide one way, the holes are continuing to slide the other way. So, you are building this up. As you build this up, clearly you have now got this sample sitting in this junction sitting in forward bias. As long as it is in forward bias, you will have a current going through it corresponding to the characteristic that we just saw here. You are now in forward bias, so you will have a current going through that sample. This is a current going internally through the sample, please keep that in mind. We have not connected anything external to the circuit, it is internal. Internal to that sample, you have current going through the sample, and it is an internal short circuit. Okay. So, it is you can think of it that way, it is an internal short circuit, internally this current is going, and that is how the electrons and holes are getting consumed. Okay. And it is behaving as a forward bias diode. So, when you simply take the solar cell and put it out in the sun, then this is the circuit that you are dealing with. The circuit that you are dealing with is that solar energy is coming in and creating this photocurrent that you see. The photocurrent is flowing through the circuit internally. So, this is not an external circuit. This diode that you see here is sitting internal. It is it's an internal diode inside that sample, and through that the electron holes are getting consumed. Okay, so it is itself powering its own self. Okay, so it is itself powering an forward bias within itself, as opposed to an external battery powering the forward bias. So, this is what happens when you put it out in the sun. Now, on this slide I would like to show you what happens when you try to take this solar cell, which is what you see on your left hand top corner, and then use it to actually do something useful externally. So, to do that, given that you know I mean by itself this is the situation it is going to face when you put it out in the sun. Over and above this, we now try to attach a external load. So, RL is your load resistor. Okay, so you put this load resistor. So, now what do you have? You have a situation where you are generating more electrons and more holes on the p side, more electrons on the n side. They have two options. They can internally do the short circuit. So, internal diode they can go and complete this short circuit. They can also go in the external circuit. Okay, so this is what they can do. So, in fact they do both. So, that is the point. They in fact they end up doing both. You have some electrons going through the external load, which does the job that you want to do, and you have some electrons going through your electrons and holes going through the diode in the forward bias, and they are also lost there. So, ideally you want to minimize what goes through that diode, maximize what goes through your external load. That is basically the idea that you want to do, but there are some restrictions, which is what this diagram is about, which shows you progressively what are all the different parameters that are involved in this process. Okay, so this is what is going on. Now, in addition to this external load, even though we have put this external load here, by nature of just the electronics of what is happening there, you are not going to have only the external load. Okay, so the current has to flow, it has to flow through that sample and come out. So, there is an internal resistance, and that internal resistance exists in any even in a battery there is an internal resistance. There is always an internal resistance, because it is not that there is because the battery is in the current path, the solar cell is also in the current path. So, if you complete the circuit, there is a physical dimension to the solar cell, the current has to physically flow through that dimension, right. So, there is a resistance associated with that. So, that is your internal resistance, so to speak, and that resistance is in series. So, you will always have a series resistance which will add to your load resistance. So, this is something that you cannot escape in this sample. So, in addition to the diode that is sitting here, you have all these additional parameters, which is this series resistance as well as your load resistance. The one other aspect that we have not accounted for here is that recombination that I spoke to you about earlier. Okay, so that recombination is even without any without this forward bias aspect of it, that does not involve any biasing aspect of it. It simply means you created electron and hole even before let us say even before the electron could go off to the n side and the hole could go off to the p side. It might get annihilated internally itself. On the p side itself they may get annihilated, on the n side itself they may get annihilated, but it is all got to do with the same solar energy that came in. So, the solar energy created all this thing, it created the possibility that you could have all this current, but some of the current basically got lost within itself, right. So, that photocurrent, some of it got lost internally because of the internal short circuit or internal recombination, so to speak, and so that is what this is. Okay, so, this is like a shunt resistor. So, it adds to the internal aspect of recombination that is going on. So, this is from the forward bias, this is from the recombination, this is the series resistance that you have, and this is the load resistor. Okay. And so, this is how the circuit looks. Okay, so, you basically buy a solar cell and you connect an external load to it. So, you buy a solar cell and you connect a bulb to it, let us say you connect an LED to it. Okay, so, then what you have done is you have taken essentially a solar cell, and you only are aware of the solar cell being present here. Okay, so you have a P and you have an N, and then you have taken this and connected it to a bulb, right. So, I am just notionally showing that here. So, you have some bulb here. So, this is what you have done internally, this is what is happening. if you take the whole thing into account, this is what is happening. Okay. So, you have lot of processes going on, you have the photocurrent that is generated, you have the diode operating internally itself, the diode is there, it is operating in forward bias, you have a shunt resistor which is representing the recombination events that are happening, you have a resistor in series which represents the idea that there is current going through that solar cell before it even comes out of the circuit, and then finally you have your load resistance. So, this is your overall circuit. Okay. So, so these are all the various parameters of how the solar cell behaves when you have incoming radiation. So, the purpose of this class was to look at how the PN junction and therefore the solar cell based on the PN junction, how does it behave with respect to the incoming solar radiation. So, in conclusion, what the main points that we see here are that the PN junction stabilizes the electron hole pair. Okay. So, this is very critical, and that is why it is preferred over simply having a semiconductor. And then the PN junction is PN junction solar cell is a current source, because the photocurrent is being generated and therefore it has to be used accordingly, and what that accordingly is we will see. How do you maximize the potential, how do you maximize the ability of the solar cell to function for a particular end use, or how do you match the end use to function to the characteristics of the solar cell. It is a little bit tricky, so we have to understand some parameters associated with, then we will understand how that matching is done, or even why that matching is required. How do you match some end use to a solar panel. It is a bit different from what you would do with respect to a battery, and that is why it is of interest. So, in summary, that is what it is. We wanted to see how it functions in the presence of radiation, and that is the detail that we looked in considerable detail through this class. Going forward, we will see something more on how it can be utilized, what other parameters come into place when you put that solar cell plus end use together. Okay. So, with that we will conclude today's class. Thank you.